Okay, let's check out notes. Week 28, part 2. This is sort of a joke right here. Ha ha ha. That's not a P, that's a row. Alright, so question number 1. Assume that the voltage of the battery is 9 volts and the 3 resistors are identical. What is the potential difference across each resistor? This might also be described as what is the voltage drop across each resistor. So these are in series. And we know that the voltages across these will add to 9 volts, and if they're the same resistance, we would expect the voltage across each to be 1/3 of 9 or 3 volts. Okay. So that was tricky. They didn't give us the voltage, but they told us that they were all the same. In the circuit below, what is the voltage across R sub 1? So we have 4 ohms and we have 2 ohms connected in series with a 12-volt battery. So hopefully you are recognizing that the equivalent resistance of the circuit would be 6 ohms. That's an ohmage symbol. And then V equals IR. What are we doing? Voltage across R sub 1. Oh, okay, well this is the long way. Here's the short way. The short way is just to think that, okay, 12 volts, right, is the voltage that pushes the electrons through these resistors. And voltage is used up in pushing the electrons through the resistors. So if we consider this has twice the resistance of this, twice the voltage is going to be taken up in moving the electrons through. And together we have 12 volts. So if the voltage breakdown, if it's 8 volts used up here and 4 volts used up here, it makes sense that twice is used up there. So that's going to be our answer. But the long way is we could actually solve for current. And so we'd get the current equals 2 amps. And then we would be saying V equals IR for each of these. And we'd get the voltage drop is 2 times 4 or 8. So that would be the long way. And lo and behold, all right, we like that correct answer. Yeah. We don't want that. Wrong button. Alright, in the circuit below, oh, this looks similar except they are in parallel. In the circuit below, what is the current through R sub 1? So what's the current through here? Alright. Tricky stuff, kind of, but kind of not. So, when you see this, you have these parallel resistors, and you might automatically start doing this 1 over R, equals 1 over 2 plus 1 over 5. And that's all fine and dandy to find the equivalent resistance, but you know that for resistors in parallel, okay, 10 volts is applied to that resistor, and 10 volts is applied to that resistor. There's this direct connection from the battery to the resistor, which means that, yeah, 10 volts across here and 10 volts across here. So if we just want to know the current through the 5 ohm resistor, I think that's what they were asking. Yeah, current through the, okay. So if we just want to know the current through here, we could be using Ohm's law, V equals IR, where the voltage across that resistor is 10, the current is I, and the resistance is 5. So, hopefully dividing we get 2 amps. Let's see what they say. Aha, bueno. Okay, next question. This is good. Points P and Q are connected to a battery of fixed voltage. There's our battery. As more resistors are added to the parallel circuit, what happens to the total current in the circuit? So, this is some kind of situation where the battery is applying a voltage to this. This is all wiring, and we're adding resistors and resistors and resistors in parallel. So, if you were to do some calculating, let's say those reach 2 ohms. All right, and I don't know, you could do this and just to prove it to yourself. But if you had this, you'll see that the more, that's a 1 up there, the more resistors we add, the less the equivalent resistance becomes. Because the more pathways there are, that means the less current passes through each, and so the equivalent resistance decreases. So, what it does ask. What happens to total current? Okay, so total current, if we have the voltage remaining constant, and what's happening as we add resistors is the resistance is decreasing. So if this is constant and this is decreasing, then this has to increase. The less resistance there is, the more current there will be. So what happens to the total current? We expect it to say this for our answer. Okay, very nice, very nice. And by the way, you can always pause and read all that stuff, and that actually might be a good idea. But yeah, to avoid making this long and rambling, I'm sort of moving quickly through it. Current flows through a light bulb. Alright, so here's current, here's our light bulb. If a wire is now connected, so pretend this wasn't here, right, and current's flowing through the light bulb, but if we connect this wire across the bulb, what happens? Across the bulb, what happens? So, if we're looking at this, previously the current was flowing through and lighting up the light bulb. So if we attach this wire, we have this in parallel, and the wire has very little resistance. So the super large majority, like all, of the current is going to pass through the wire. This is called a short circuit. Short circuit. So that's when there's a direct path for the current to flow. What would happen is all the current would go. Let's try this. Yeah. All right. Here's the current. And the poor light bulb would be all dim, yeah, and receive no current. So what are our answer choices? Well, what did you choose? Cool, that's what I chose too. So all the current would flow through the wire, and the light bulb would go out. We've definitely got some questions in here about light bulbs and whether they would be lit or not. Oh, here we go. So, short circuit number 2. Oh, that said short circuit. Alright. Two light bulbs A and B are connected in series. A and B are connected in series to a constant voltage source. There's our voltage source. When a wire is connected across bulb B, A will glow brighter, just the same, dimmer, go out completely, explode. That sounds fun. Whee! Alright. So, there's some voltage. Ooh, we got the big marker. There's some voltage across here and some voltage across here. This is before. So before the wire is here, pretend the wire's not there. Alright. There's some voltage drop across bulb A and some voltage drop, meaning voltage used up, across B. Okay. Then, when we actually. Okay, fine. When we put the wire in there. This, by the way, right here is a switch. So assuming the switch is closed so that current may now flow, the current, and I should draw this correctly because the current actually, here's our positive. Okay, so we say that current goes this way, and the current would go like this, and the current would go like this, and the current would go like this. So the equivalent resistance of the circuit has now decreased. Right? Because we used to have this in there, but now we don't. So if the resistance has decreased, then the current would increase. And if there's more current flowing through the light bulb, what do you think? Let's see. Explode? Well, probably not, but who knows? Let's see. But hopefully it says glow brighter than before. Let's see. Ah, good. And they kind of describe what we just talked about. So you could pause and read that. Might be good. The 3 light bulbs in the circuit. So 3 light bulbs all have the same resistance of 1 ohm. By how much is the brightness of bulb B greater than the brightness of bulb A? So is it brighter or not as bright as bulb A? These are what we're looking at. This guy and this guy. Okay, so we have this and this in parallel, right? So 10 volts is applied between these 2 points, and 10 volts is also applied between these 2 points. And did it say they all have a resistance of 1 ohm? Yeah. Okay, so if we were to say, we could say that this is a 2 ohm resistor, because those are in series, and we could say that this is a 1 ohm resistor. So if we just consider, well, how much current is going to flow through these things, right? Through here, we're going to have 10, that's a lot, 10 amps. This one might explode. Through here, we're going to have 5 amps. How did I get that? From the V equals IR, right? We got 10 volts, 2 ohms, and current giving us the 5 amps. So if this light bulb is getting more current than this light bulb, it should be brighter. That's the bottom line. Let's see. And, oh, right, there's more to it. We have to say how much. Okay, so what was our formula for power? I think we had this one, V squared over R. And this was the one that didn't, well, whatever. We just calculated the current. So let's just go ahead and use this. This is the formula we know for power. And so for bulb A, we would have a current of 10 times a voltage of 10, so 100 watts. And for bulb B, we have, okay, this is good. We have a current of 5 amps times 5 of the volts is used up here and 5 of the volts is used up here. So, yes, we said there's 10 volts from here to here, but notice how that's a voltage drop over here and over here. So, we would only have 25 watts going, or bulb B would be drawing 25 watts. So let's see. By how much is the brightness of B greater or smaller? So B is 1/4 as much. Let's see what this says. Oh gosh, I was getting worried about that one. Okay, cool. So here's a calculation, which is basically what we just did. Cool. Alright, what happens to the voltage across the resistor R1 when the switch is closed? So here's an open switch, meaning the current's going to go like this, okay, through this one and this resistor. And then when the switch is open, all of a sudden there's this parallel path. Part of the current goes this way, part of the current goes this way. So what happens to the voltage across resistor R1? When the switch is closed, the voltage will. So voltage across, battery supplies some voltage. Some of it is used up here, and then some of it is used up here. So if all of a sudden the switch is closed, we now have this parallel path. Some of the current goes that way, some of the current goes that way, and this resistance is now something less than R3. So let's call it R4, and R4 is pretty small. Okay, so if there is less resistance here, then we can say that because R1 has stayed the same, we can say that the percentage of the voltage drop across here, more will be used up here because less is needed here because the resistance is smaller. So if that made sense, great. Yeah, well, that's how I can explain it. Dang, I hope that worked. So let's see. What happens to the voltage across R1 when the switch is closed? The voltage will. So it should actually increase. And you know, if you have a situation like this and the whole increase, decrease, that's not really making sense, you could just make up some values, you know, and make them nice, neat values. I call this 4 ohms, and then you have maybe a 1 ohm and a 2 ohm or something like that. And then you have actual numbers that you could calculate, and it would involve a lot more, but it should increase. Yeah, there we go. Let's see how they explain it. In addition, it decreases the equivalent resistance. Okay, that's what we talked about. So the current from the battery increases. Alright, so if this, right, the resistance here decreases, so there's all of a sudden more current, and then if you were doing V equals IR, right, the resistance of this guy is the same. It's not really male, but the resistance of that resistor is the same, and so the current increases and the voltage drop across it would increase. I like Okay, we're getting there. Which resistor has the greatest current going through it? Ah, yes. Assume all resistors are equal. Okay, so we definitely needed to know that. But you see variables, not numbers, and so you panic. No, don't panic. No panic. No numbers, don't panic. We got this. So, we can talk about it this way. Let's zoom in. We're looking for greatest current. All right, so current comes out of the battery and goes whoosh, and goes whoosh. All right, if these are both the same, well, let me start by this. The current that passes through here is the same as the current that passes through all of this, is the same as the current that passes through the wire. So there's some current that does this. We're just going to call it I, and I passes through there, and I passes through there. If these resistors are equal, half's going to go this way, half's going to go this way, and the current through these would be the same. Okay? So that current comes together, and we have I worth of current right here, and then that current has a choice. Hey, we can go this way, or hey, we can go this way. Okay? And when they look at these two paths, this path has twice the resistance of this path. So less resistance here means, and I'll try to draw this to scale, so we have some current that goes this way, but we're going to have more current that goes this way because there is less resistance. So half and half, and more than half and less than half. So it turns out this one, R sub 5, is the one that's going to get most or more current than any of the other ones. Look at all those answer choices. And let's see. You might want to pause and read that. I don't know how they described it, but I think it was similarly. What is the current in branch P? Okay, so this is sort of a lead-in. Current in branch P. This is a lead-in to what are called Kirchhoff's loop rules that we'll get into next week. But basically, if there's 5 amps coming down this way, and right here there's 8 amps in the circuit, you know that here there have to be 3 amps that are adding together, right? Just think of people walking down the hallway. So 8 amps come to this junction. Okay, these, where the wires split, we call these junctions. And so if 2 amps is going this way, we know that 6 amps should be going that way. So that's a little introduction to these loop rules that we'll get into next time. But junction, that's just a place where sort of roads diverge. And I got 6 amps. Alright, ammeter. What does an ammeter do? Measures current. Exactamundo. Ammeter A is connected between points A and B. Alright, and this is our last one, and I just thought I'd throw this in there. There's no specific concept that we've learned about this, but I think you can get it. Ammeter A is connected between points A and B in the circuit below, in which the 4 resistors are identical. Again, we like that. The current through the ammeter is. So, voltage, some current flows, and it gets to this junction, right? And it can go either way. Because the resistances are the same, we're going to go halvesies, okay? Half the current goes this way, half the current goes this way. And so the current gets to this junction, it's like, hey, I can go this way or I can go this way. And current here goes, hey, I can go this way or I can go this way. So the fact that this is open to both paths means it kind of cancels out, and all of it would continue like this, and all of it would continue like this. So the current through the ammeter in this case would be nothing, or 0 amps. We can also describe these as equipotential. Equipotential, not surfaces, but equipotential regions, meaning the voltage at both of those spots is exactly the same. And if the voltage is exactly the same, there's no push on the electrons to move it through. It's kind of like 2 objects that are the same temperature, right? If they come into contact, they're not going to exchange heat. Alright, so anyway, I thought I'd throw that one in there, and hopefully that made a little bit of sense. You could read what they have to say. Thus, the potentials at points A and B are also the same, so that's cool. Potential meaning voltage. Thanks for listening.